Now let's put all this information together and see how it's going to help us solve a differential equation. So we want to solve the differential equation y double prime minus 6y prime plus 9y is equal to t squared e to the 3t. Our first step is to take the Laplace. And when we take the Laplace of both sides, that's really going to equate to taking the Laplace of just each piece separately. So remember, this guy came from a theorem from the last section. When we take the Laplace of y double prime, that's going to be s squared y of s minus s times y of 0, or we could say f of 0, either one, minus s to the 0 y prime of 0. If we substitute in everything we know, our y of 0 is 2, so this is a 2s, and then our y prime of 0 is 17. So this is going to be minus 17 times 1, which is minus 17. Plus of y prime was s y of s minus s to the 0 y of 0. Substitute in what we know. We know y of 0 is 2, so this is 2 times 1, which is just 2. The Laplace of y is equal to y of s. And then when we take the Laplace of t squared e to the 3t, that's going to require our s translation. So we could view this as t squared as long as we remember to take s to s minus 3. So if we use our tables, we're going to use number 3. Our n is 2, so it's going to be 2 factorial over s to the 3rd. But because this is a translation along that s axis, we need to change that s and replace it with an s minus 3. 2 factorial is 2. So we can rewrite the Laplace of t squared e to the 3t as 2 over s minus 3 quantity squared. So now we have all those pieces. Let's substitute it into this guy. So if we make our substitution, we have the Laplace of y double prime, which is that, minus 6 times the Laplace of y prime, which is that, as y of s minus 2, plus 9 times the Laplace of y, which is y of s, and that's equal to the Laplace of t squared e to the 3t, which is 2 over s minus 3 cubed. So let's work this out. Remember, the goal is to solve this for y of s and then take the inverse Laplace. So we're going to do some fancy math here. Let's distribute that negative 6. So I'm going to group these terms together. Notice all three of those have that y of s in common. So I'm going to go ahead and factor that guy out. And when I do, that's going to be left with an x squared minus 6x plus 9. Now I'm going to go ahead and move the other terms to the other side. So I'm kind of doing 2 or 3 steps in one here. So to move that 2s, I need to add 2s to both sides. And then we have a negative 17 plus 12, so that's a negative 5. So to move that to the other side, we would add 5. So now that s squared minus 6s plus 9 factors into s minus 3 times s minus 3, which is s minus 3 squared. Nope. The exponent on this guy, remember, is a 3. That's a miswrite. Let me correct that. So just to kind of draw your attention to that, we had a cubed over here when we found the Laplace of t squared e to the 3t. So that cubed has to stay here. Just kind of followed it down. And now we're going to divide both sides by the s minus 3 quantity squared. And when we do that, we're going to have 2 over s minus 3 to the 5th here. And then we're going to have we do 2s plus 5 over s minus 3 squared. So this guy is going to require partial fractions. We're going to want to simplify and see what happens. We won't know if it really simplifies until we try it. So this is a repeated linear in the denominator. So there's our setup for repeated linear. So 2s plus 5 would be equal to a times s minus 3 plus b. Notice that this b term already has that denominator we're looking for, so we do not need to multiply by anything. So our system, 2 is equal to a, and then 5 is equal to negative 3a plus b. So if we know 2 is a, and we substitute that in here, then that tells us that b is going to be equal to 11. So this right-hand side, we can rewrite this second term as 2 over s minus 3 plus 11 over s minus 3 quantity squared. So there we are. Now we've got to take the inverse Laplace. So we're in Laplace world. Now we have to go back home to our regular rectangular world. So I'm going to write this step out. This is important because it will show you what we're thinking and that process we're thinking about. So it lets the reader know about the S translation. So there we go. Now, when we take the inverse Laplace of y of s, we're just going to get y of t. This isn't quite in that form yet, so I'm going to rewrite that as s to the 5th, recognizing that s minus 3 we're replacing with an s. And that lets us know that whenever we find this, we're going to have to multiply it by e to the AT. This guy does have a formula. We could also use an S translation for that, and I want to show you how that's going to work. So let's just do that same kind of concept. You've got two ways to approach this one. We could think about this as 1 over S, recognizing this is going from S minus 3 to S, which means it's going to be multiplied by an exponential. And then same thing here. 1 over S squared, recognizing that we replaced S minus 3 with an S, so we're going to have to multiply by an exponential there. But all three of these we can view as S translations. And like I said, this middle one, we could view it as an S translation, or we could go ahead and evaluate as is. I just want to show you that you can view it as an S translation. So if we look at this first one, we want 1 over S to the 5th. So we could view that S to the 5th as S to the 5 to the 4 plus 1. And if we look at our sheet over here, that's going to match up really closely with that number 3. We just got to figure out what our n is. And if we rewrite that exponent as 4 plus 1, then we see that that n is going to be 4. However, we are missing that 4 factorial in the top. So we can multiply it in as long as we divide by 4 factorial somewhere else in the problem. This guy, if we evaluate, going back to our sheet, 1 over S is just 1. So let's just kind of simplify what we have here. We have 2 over 4 factorial. 4 factorial is 4 times 3 times 2 times 1. So you can see how those 2's are going to cancel, and that's going to give us a 1 over 12. This guy we said was going to be t to the 4th. But we have to apply this, and that means we need to multiply it by e to the AT. So that first term is going to be 1/12 t to the 4th e to the 3t. The second one, this guy ends up being 1, but we can multiply it. We have to multiply it by e to the AT. So we're going to end up with 2e to the 3t there. Now we would have gotten the same thing if we would have just used the definition for 1 over s minus a. So you've got two ways to view that. That's rule 11. And we would have ended up with e to the 3t there. So there's multiple ways to view all of these. And then this last one. So we can view that exponent here as 1 plus 1. So we could think about this in terms of rule 3. It's probably going to be easier to think about in terms of rule 2 though, because we just have that 1 over s squared, and that's going to give us that t value. We would have gotten the same thing using this one. That's what I was initially thinking. We would have a 1 plus 1 here, and then a 1 factorial up here. And that would give us a t to the 1st. So this is going to be 11 times t, and then recognizing that this needs to be multiplied by e to the AT. So here's our final answer for this guy. Okay, notice this does give us the particular solution. We've talked about that before because it uses those initial conditions in the beginning when we find the Laplace of y double prime and the Laplace of y prime. So there's our final answer. Let's do another one. So let's take a look at one more of these. So our first step, like before, is that we're going to have to take the Laplace of both sides. So that's going to involve us taking the Laplace of y double prime, the Laplace of y prime, the Laplace of y, the Laplace of 1, and the Laplace of e to the negative t. So the Laplace of y double prime, that goes back to a theorem in the last section. That's s squared y of s minus s y of 0, or we could say f of 0, minus y prime of 0. So if we make our substitutions for y of 0, we're going to get 0. For y prime of 0, we're going to get 0. So this is just going to be s squared y of s. The Laplace of y prime is s y of s minus y of 0. Our y of 0 is 0, so this guy's 0. So we're just going to have s y of s. And then the Laplace of y is just y of s. Laplace of 1, if we go back to our cheat sheet here, the Laplace of 1 is 1 over s. And then we're going to need the Laplace of e to the negative 1t, which is going to be 1 over s plus 1. I'm going to write that one over here. So then when we make our substitution, we have the Laplace of y double prime, which is s squared y of s, plus 4 times the Laplace of y prime, which is s y of s, plus 6 Laplace of y. I miswrote this. We need a 6 there. Laplace of y is y of s is equal to the Laplace of 1, which is 1 over s, plus the Laplace of e to the negative t, which is 1 over s plus 1. So notice that on the left-hand side, we can factor out a y of s from all those terms. And that's going to leave us with s squared plus 4s plus 6 So I'm going to get a common denominator over here. Here's why I want to do that. I know I have to divide both sides by this, right? And when I do that, instead of having to do partial fractions twice, because remember, this guy's going to be in the denominator for each one of these. So instead of having to do partial fractions twice, once on this term and once on this term, I can just do it once and do it on this combined fraction divided by that guy. It's just going to make life, I think, a little bit easier. We'll see if it's easier. So if we were to combine these two fractions, we need to multiply that first one by s plus 1 and the second one by s. So that's going to give us an s plus 1 plus s over s times s plus 1, which is going to give us 2s plus 1 over s times s plus 1. So now if we divide both sides by that s squared plus 4s plus 6, we're going to have 2s plus 1 over s times s plus 1 times s squared plus 4s plus 6. And that's going to require partial fractions. So let's do partial fraction decomp. So we have a linear times the linear. This guy is an irreducible quadratic. It's not going to factor very nicely. It's not going to factor over the rows. So in that numerator, to keep this as a proper fraction, and proper means the degree of the top is less than the degree of the bottom, we have to consider a linear in the numerator. So that first term is missing the s plus 1 and the s squared plus 4s plus 6. The second one's missing the s and the s squared plus 4s plus 6. And then that last one is missing the s times the s plus 1. So let's do some fancy math and multiply some things out. So if I were to distribute here, and I'm going to actually come up here and do that. So I'm thinking about this right-hand corner as my scrap piece of paper. So I'm going to have s cubed plus 4s squared plus 6s. And then when I distribute that 1, I'm going to have an s squared, and I'm just going to line them up vertically, plus 4s plus 6. So I have s cubed plus 5s squared plus 10s plus 6. B, if I distribute that s, I have s cubed plus 4s squared plus 6s. And I'm going to leave that a out. I know everything in here needs to be distributed by the a. I know everything in here needs to be distributed by the b. This guy, I am going to have to factor this out. So this is cs plus d times s squared plus s. So now if I were to FOIL everything through, I have that. So let's come up with that system of equations. Remember, this guy's equal to 2s plus 1. So we have coefficients for s cubed, s squared, s, and then that constant. So if we look at coefficients of x cubed on the left and on the right, on the left we have 0. On the right we have a plus b plus c. S squared, we have a 0 on the left. We have a 5a on the right. Plus 4b plus c plus d. For s, we have a 2 on the left here. We have a 10a, 6b, and then a d. And then the constants on the left, we have a 1, we have a 6a, on the right, and it looks like that's the only thing we have. So we've gotten a system. We had 4 variables to begin with. To solve, we have to have 4 equations to get a unique solution. These will always give a unique solution. So if we were to type that in the calculator, we're going to get the identity on the left. I got 1/6, 1/3, -1/2, and -5/3. So then our y of s, if we were to substitute all of that in, is equal to 1/6 over s plus 1/3 over s plus 1 plus -1/2 s minus 5/3 over s squared plus 4s plus 6. So now we've got to deal with that guy. So eventually we're going to have to take the inverse Laplace. But before we do, we're going to have to split the numerator for that last term. So I'm going to write this as a minus 1/2 s over s squared plus 4s plus 6, and a minus 5/3 over s squared plus 4s plus 6. So now let's take the inverse Laplace. So if I'm going to write this step out, it's going to look like this. I'm going to go ahead and factor those constants out. So this guy's pretty easy. This guy's pretty easy. Those are straightforward, straight from the table. This one and this one's going to take a little tweaking. So let's go ahead and write in everything we know. And then we'll tweak what we need to where necessary. The inverse Laplace of y of s is y of t. The inverse Laplace of 1 over s, going back to our sheet, 1 over s is 1. The inverse Laplace of 1 over s plus 1, that's going to be our number 11 over here. Only our a is going to be a -1. And then we're going to have to tweak these guys. So if we look at this guy, it doesn't really match any of our formulas. So maybe it's an S translation. This guy doesn't factor under the rails, so we can't break it down anymore. But what if we try to complete the square? So let's do that up here. We have s squared plus 4s plus 6. So remember, when we complete the square, we're going to add and subtract something. So we're really adding 0 there, which does not change the problem. We always take half the middle term and square it. Half of 4 is 2. 2 squared is 4. If I add 4, I have to subtract 4. That allows us to rewrite this, because that will always be a perfect square trinomial. And then this guy is going to end up being a plus 2. So we can rewrite that piece as s plus 2 squared plus 2. And then the second piece we can rewrite as s plus squared 2, s plus 2 squared plus 2. Now, this guy, let's think about that group s plus 2. For this to match, this is similar to that cosine formula. For this to match that cosine formula, we really have to have a plus 2 in the numerator. But if I added 2 in the numerator, I have to also subtract 2. So that piece we can rewrite now as the inverse of Laplace of s plus 2 over s plus 2 quantity squared plus 2. And then we're going to have a minus 2 inverse Laplace of s plus 2. Just kidding. We're splitting that numerator, so that's going with that first one. I factored that negative 2 out. Now I have a 1 up there. Then we have minus 5/3 here. Inverse Laplace of 1 over s plus 2 squared plus 2. Now, this guy now looks like my cosine formula. This is really going to be the sine formula. We're going to have to do some tweaking. I'm not going to write this out yet until I can combine these terms. When we split the numerator here, that Laplace was all multiplied by a negative 1/2, so it will have to distribute to those two pieces. So lots of math going on in the background. Negative 1/2 times a negative 2 is a positive 1. And then we have that 5/3 inverse Laplace of 1 over s plus 2 squared plus 2 here. And then these we can put together. So doing some of these is kind of like playing chess. We need to be able to see a step or two ahead. And the more you do these, the more you're going to be able to see that. It's one of the fun things about math. So 1 minus 5/3 is a minus 2/3. Now we can see this guy's an S translation. We have the same thing here and here. So if we were to replace this with an S over S squared plus square root of 2 squared, we see that we took S plus 2 and we replaced it with S. So that tells us we're going to multiply that cosine by an exponential. Same kind of thing here. Laplace inverse. We could view that as S squared plus square root of 2 squared. Taking S plus 2, replacing it with S. Okay, so this almost fits that sine formula. If you remember, that sine formula has to have a k in the numerator, and our k is square root of 2. So we actually need to multiply by square root of 2 here and compensate with a 1 over square root of 2. So then when we rewrite this guy, this is going to be cosine of kt. This 2 divided by square root of 2 is a square root of 2. So now we have that reduced to square root of 2 over 3. And this is sine of our kt. So these other pieces, they were still there. We didn't worry about those. My final answer, let me clean this notation up just a little bit. It's going to be y of t is equal to, that first term was 1/6. The second term was 1/3 e to the negative t. The third one ended up being negative 1/2 cosine of 2, square root of 2t. And then we have to show this. Don't forget this guy. That tells us it needs to be multiplied by e to the negative 2t. And then that last one ended up being minus square root of 2 over 3, sine of 2t, and then we need to show that S translation, e to the negative 2t. So there's our final answer for this problem.